Good morning, students. Last time we have seen about electric charge, electric current, and Ohm's law. So, electric charge, that is nothing but electric energy which passes through a conductor. Then electric current, that is the electric charge passing through a conductor per unit time and perpendicular to the cross-sectional area of the conductor. And Ohm's law, that is V is equal, means potential difference V, that is directly proportional to the current. So V is proportional to I, so V is equal to I into R, where R is a resistance of the material. Now we'll see about this resistance of resistance dependence. So resistance dependency, it is further portions of the Ohm's law, based on Ohm's law. So it says about, if we take a conductor of having conductor which is having a length of L and conductor is having length L, and for this conductor we will get the resistance R1 is equal to V upon I as per Ohm's law. Same way, another same conductor with the same length L, suppose it's having a resistance R2 is equal to V upon I. Now, if we combine both these conductors with length L and N, so if we take both these conductors together with length L and L, that is equal to 2L. So its total resistance will be R1 plus I2. So V upon I plus V upon I, that is equal to 2 times V upon I. And V upon I, that is equal to R1 or R2. So, and R1 and R2 both are same. So is equal to 2 times R1. So we can say that if length of the conductor is doubled, its resistance will be doubled. So R is proportional to L. Okay. So here in this case, what we did just increase in length, that will increase in length, that will increase the resistance of the conductor. So as the length is double, the resistance will be, final resistance will be doubled. Okay. Same way, if we are taking, and actually I have just explained the concept so that you can understand, but the theoretical explanations and the details is given in a PDF, so you can see it inside the PDF and you will get the you will understand the concept. Now, as we get R is equal to 2R1 when the length is doubled, same way we will derive this. This is equation 1, R is proportional to L. Now for area. Okay. So suppose this is a conductor which is having a length L and the another conductor with the same length and the same material, both are kept together. So this is A and B, and the potential difference between A and B, that will be same. So the total resistance for this conductor R is equal to V upon I. Okay. So here in this case, but the resistance R1 is equal to, so in this case we take the lower portion and upper portion of the conductor. So this is a lower portion and R1 and this is the upper portion R2. Okay. So here the potential difference between A and B that will be seen, and the resistances R1 and R2 and the current which passes through the A and B, so that will be divided. So R1 is equal to V upon I, but as the current is divided here, for the lower portions we will get current I is equal to I by 2. Same way I2 is equal to V upon I by 2. Okay, so here the resistance R1 is equal to V upon I by 2 is equal to 2 times V upon I, and V upon I, that is total resistance R, so is equal to R1 is equal to 2 times R, so R is equal to R1 by 2. So if the area of the conductor is doubled, the resistance to the conductor will be half. So R is proportional to 1 upon A. So this is our equation 2. Now from equation 1 and equation 2 we will get, so from equation 1 and 2, R is proportional to L upon A. So if we remove this proportionality, so we can write R is equal to rho L upon R, where rho is what? It is a resistivity which depends on the pressure and temperature. Okay. Now as per Ohm's law, we have the equation V is equal to I into R, but the resistivity, new terms. So R is a resistance, rho is a resistivity, and that resistivity depends on pressure and temperature. As the temperature is increased, the length will increase, and that will increase the resistance. Same way the pressure is applied, the area is reduced, so the resistance will increase. So that is the effect of pressure and temperature. Now V is equal to I into R, that is Ohm's law. So I is I into rho L upon A. So V is equal to I into rho L upon A. So that is Ohm's law. So this is our theory for a resistance dependency based on Ohm's law. So you can take a screenshot of this page, and now we'll move on for a further topic. Now our next topic is the relation between E, electric field, epsilon, conductivity, and current density J, where E is the electric field, epsilon, that is the conductivity, and third one is the current density J. So we have to derive the relations between these 2, 3, electric field, conductivity, and current density. So here in this case, we will use one equation, that is in your chapter number 1, V is equal to E into L, and we have another terminology, that is conductivity. So we will initially write potential difference V is equal to E into L, where E is the electric field and L, that is the length of a conductor. Okay. Now conductivity, epsilon, that is equal to 1 upon rho. Rho, that is a resistivity. Rho is a resistivity. Now we'll see about the current density. Means the third terminology, that is the current density, that is denoted by the symbol J. Okay. Sorry. Okay. So here is a conductor. Suppose the electric current passing through this point. So electric current passing through the point perpendicular to this cross-sectional area, that is known as the current density, or we can say that electric current passing through a point in a conductor per unit area perpendicular to that point is called current density. So electric current upon cross-sectional area A per unit area. So J is equal to I upon A. Unit of I, that is ampere, and unit of area, that is meter square. So ampere upon meter square, that is the unit of a current density. Okay. Now for this conductor, as the electric current will pass, so the electric field will be produced inside this conductor. So for any uniform electric field E, the potential difference across the conductor of length L is, so here this is length L of the conductor. So potential difference V is equal to, we will use these equations over here. So V is equal to E into L. E is the electric field and L is the length. Now from Ohm's law, V is equal to I into R. So I into R is equal to E into L. So we put the equation of R, I into rho L upon E is equal to E into L. So L will get cancelled and I upon E, that is the current density J. So J into rho into J, that is equal to E. So J is equal to E into 1 upon rho, and 1 upon rho, that is conductivity. So E into epsilon. So J is equal to E into epsilon. So this is the relations between current density, and in a vector form, J is equal to E into epsilon. That will be the relations between electric field, current density, and conductivity of the material. We have these equations where current conductivity, that is the ratio of, that is the reciprocal of a resistivity rho. Now we'll see about the new terminology and the new concept of the chapter, and that is drift velocity. So we will see about the drift velocity and its equation. So our next equations, or the next topic, that is drift velocity, that is denoted by symbol Vd. So to understand the concept of drift velocity, let's take the conductor. This is one of the conductor. Now for this conductor, suppose no electric field is applied to the conductor. So when no electric field is applied, so the net resultant velocity, when E is equal to 0, so the electrons inside the conductor, so net resultant velocity of the electrons, free electrons, that will be equal to 0. And we have seen about the same concept in your last class. So here V is equal to 0. Net resultant velocity is 0 when no electric field is supplied or applied. So in that case also the current will be 0. Now if I connect this conductor with the external battery, so I am connecting this conductor with external battery, plus minus, this will be plus and this will be minus. So because of the external battery, the positive charge that will passes from the positive side, positive charge that will passes from the positive side towards the negative side. So this will be the plus, 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 plus. So here this positive charge will move towards the negative charge. So when the external battery is connected with the conductor, the charged particles from this positive side is being continuously pushed. Charged particles from this positive side is being continuously pushed towards the negative side or negative ions. So this velocity of this charged particle is called drift velocity. This velocity of this charged particle is called drift velocity. Same way, another concept, suppose this one is a positive charge. Now if we take an electron, suppose this electron collide with this positive charge, and after collision it moves back. Okay. Same way, another electron that will collide with the same positive charge and it will move back. So during this process, this average time required for back-to-back electron collision with positive ions is called relaxation time. So here back-to-back electrons, the time required for back-to-back electrons collision with this positive ions, that's called relaxation time, that is tau. And in this drift velocity concept, we'll use one equation from the first chapter. F is equal to E into small e. F is equal to E into E. Okay, where E is the charge of electrons and capital E, that is the electric field. So this is the electric force F. So here in case of a drift velocity, as the current is supplied through the battery in case of conductor, so obviously the electric field will produce. So as the current is supplied, electric field is generated. So electric force F is equal to E into small e. Okay. Here in this case, this is a direction of current, that is plus to minus, and the direction of electron force, that will be minus to plus. So we will take a minus sign over here. So F is equal to minus E into E. So from Newton's second law of motion, F is equal to M into A. So this is equation 1, this is equation 2. So MA is equal to minus E into E. So A is equal to minus E upon M. So this is the equation of acceleration. Now you can take a screenshot of this page if you want, then we'll carry ahead. Go ahead. Okay. Now we have the equation A, acceleration A is equal to minus E into E upon M. So in vector form, we can write this equation as A is equal to minus E into E upon M. Now we have seen this concept that suppose this one is a positive ion and the electrons that collides with this positive ion, then it will move back. So after collision, this electrons is having a initial velocity ui equal to 0. So after collision, initial velocity of electron ui is equal to 0. Okay, so vi is equal to, this is your equations, kinematic equations, ui plus a into t. ui is equal to 0 and a is equal to minus e into e upon m into t. So this equation we have used. So vi is equal to minus e into e upon m into t. So that is equal to Vd, that is known as a drift velocity, and this in vector form. So in scalar form, Vd is equal to minus ee upon m into t. So here is your equation for a drift velocity. Okay, so here we have derived the equations for a drift velocity and the explanation of a drift velocity. The remaining theory of the chapters and the PDF which is attached here with that I will carry it out in your next class, because it's already about 22 minutes completed. So just try to understand the concept, and if you have any doubts, any query, you can WhatsApp